start the actual the program for the conference with the plenary talk by Professor Dror Fixler. Professor Fixler is the director of the Institute of Nanotechnology and Advanced Materials, BINA, at the Bar-Ilan University, Israel, a professor in the Faculty of Engineering. And his bio is already in your program. He has done a significant work on electro-optics and photonics. His primary focus is developing new technology for super resolution microscopy, medical testing, and communication network. So may I request Dror to give his plenary talk. Thank you, Dror, coming all the way from his.
So thank you very much for this nice introduction. Thank you everyone that joining us today. My name is Dror. I'm coming with my colleague, Dr. Yossi Tal Yosef, far away from Israel with my daughter here. This is my first time in Waterloo. Only one time I visited Canada before. And my talk will be split into two parts. I will start shortly about presenting our Nano Center because we did this long way in order to establish something much larger than what we have today. We already did and doing a lot of activity with CD Nano and Ben Eggleton and his colleagues and names he mentioned. And they already visited us and we are doing a lot on specific topics. We came here in order to do something similar with you as Waterloo and with all the colleagues that we have here online. And then we will go to the more interesting side, personal from my perspective, the research and the results, but I think it's something that comes together. We need to do and make good things for everyone, and then you can do amazing science by yourself. And a smart person told me in the past that a good talk start with a joke and end with a joke, and the times between the two jokes should be as short as possible. But I have 45 minutes, correct? But I will start with a joke, and I will introduce myself in different perspective. I'm engineer. Today I'm from the Faculty of Engineering. But as you heard, you got my biography, and I started as a physicist. And then I go to computer science, and then more practical aspect of engineering. And you ask yourself, are you doing theory? Are you doing practice? What are you? So you know very well that there are two types of people, of human beings. The first type are people that know to explain you everything. They know what's happened to the atom at the 10th level of the hydrogen and when he's moving there. And then if something is not work and you are asking them to solve it, they don't know. So they know everything, but it's not working for them. But there is the opposite type of people. If something is not working, immediately they are fixing it. You will ask them, what's happened? What have you did? They don't know, but it's work for them. So this is the opposite type. It's work, but they don't know why. And one type, it's know everything, but it's not working for them. So I choose to be engineer. This is a perfect matching between types of people. In my lab, nothing is working and I have no idea why. And this is what I'm going to talk with you today. So let's go to the first slide, how we are operating that. First to turn on, you see, it's a practical aspect. So I will start with the part of our BINA Bar-Ilan Institute of Nanotechnology and Advanced Material. If you can move it by hand at the beginning at least, of it's not, you know, it's not real presentation, only one slide, and then, no, it's true. So, and going, thanks, back. So, for the busy people of you that don't have time, in one slide we can summarize what we did, but this is only part of the activities that Israel as a country did during the last, from 2007. We invest a lot of money in nanoscience and nanotechnology in order to make things good for everyone. Not only research, not only industry, it's combination of all of them together. Our center including 70 PIs, professors. And we are doing research with the students, not taking care about first level degree at all, only master, PhD, and postdoc. And these are the numbers. We are proud on tens. We have 22 PhD level and more employees in our centers that we are paying their salaries, Yossi and myself. And you can see a lot of activity. We have Nano Art Museum. When you will come to visit us, you will see this unique combination of science and art as a museum, thousands of publications, patents, companies, and few hundreds of collaborations. We have hundreds of collaborations with industry that they are working with us and doing activity together for the goodness of the world. And collaboration with other universities. I will highlight few of them later on, and I hope to add you to this list. You will see already Sydney Nano there. We have equipment that we purchased for $47 million. And this equipment is for all PIs, all students, all companies in Israel in order to make startups more sustainable, in order to do big impact. And I'm proud to tell you that our equipment today working 80% utilization, almost 24/7. Although we are Jewish Orthodox, on Saturday, Shabbat, we are trying not to work. We have a lot of people, and it's continuous. The work is continue all the time. Why not? Because we have the facilities. And another nice number of 400, sorry for that, $200 million of research fund of our PIs. It's average of $230,000 per year. It's an egg chicken questions, whether the good PIs joining us or we are making them good, but who is care if these are the results. Very recently, we recognized as a DIH, Digital Innovation Hub of the European Union, of the EU. It's part of the Horizon Europe program, and we are the only hub in Israel and only few in nanotechnology, nano center in the world that recognize, and we are doing a lot of activity inside our institute in order to apply to EU programs. These are our 70 PI professors that leading the research. And maybe you are recognizing part of the faces. They are coming from 4 different departments and faculties. Life science, we have life science in our nano center, it's unique. Chemistry, physics, and engineering. We have a triplex of 3 buildings, 9 floors, and on each floor we have mixing of all PIs together. And the students working together have the challenges, the homework, all activity, and it's make collaboration in totally different size that you cannot imagine, and we are real multidisciplinary. And this is my colleague, Dr. Yossi Tal Yosef with us, and he's managing all of these people. And here you can see part of the faces and lines that connecting them. And each line, it's not a story, we are collaborating. It's paper or grants that they apply together. Different departments, our own doctors that working on the equipment, working together in order to get grants, to get papers. We split our $47 million equipment to 3 departments. You can see part of the equipment, you can mention facilities that exist everywhere, same time, no doubt. We have unique equipment like nanoscribe, like special cryo EM for life science, the only one civil ion beam accelerator in Israel. It's located in our center in order to do surface analysis and more. But the power of our center is not the equipment. There are plenty of rich groups and countries than us. You can find in China, you can find here nearby in the United States, they have everything, but they need to collaborate. You need that the operating of the clean rooms will sit together with the microscopy, with the analysis. And in our center, we have weekly meetings that we are sharing all works that we are doing for master students, Nobel Prize professors, or companies, and we are trying to help them from different angles, and by that we are providing full ecosystem to all users that coming to our center. These are the topics that we are covering, and you can see here all things that deals in the STEM and the state-of-the-art points. Recently, we established the Bioconvergence Center that combining engineering, big data, and health, that including life science and medical. The quantum, it's the next generation, the next order of nanotechnology. It's under our roof. And all the regular, like nanomaterials, clean tech, photonics, and much more. These are part of the nano centers that we are already collaborating on. Each one of them, we have a reason why we are working with them. Maybe there are binational grants between the countries, and we build a bridge between our PIs with them in order to get more money from this funding. Other part goes to sabbatical. And we have very nice program with Sydney Nano already on their flagship, 3 flagships that we are helping them as part of their projects. And I have in my focus what we are planning to do with you, and hope to discuss it tomorrow, and if it's needed, even the day after. Now let's go to the more scientific part, and this is the reason you invited me to deal about nanomedicine and what kind of activity can we do with nanophotonics in the field of medicine. And these are the topics that we are covering in my lab. You know, the hot, we have more activity. Let's say this is 60-65% of the activity. We have sensing, remote sensing. We are working with the Israeli Defense Force to detect fishing net in water. It's a very serious problem for autonomous vehicle inside the water that cannot see this kind of fishing net. But today we are focusing on nanomedicine, and the hot word is theranostics, the combination of diagnostic and therapy. And in diagnostic, we are using really all tools, goes from diffusion, reflection, spectral, wavelength, and time-resolved fluorescence imaging. We will focus on that, on fluorescence lifetime and anisotropy decay. And it goes to therapy, it goes to application, it goes to practical. Where in medicine, like detecting cancer or arterial vascular disorders, cell tissue manipulation, it's a very nice word for cosmetic. It's huge business, a lot of money, and we are doing a lot of activities in this field, and this is some kind of application for this kind of technology. But today we are going to talk a little bit about the background of how we are going to implement biological logic gate computers inside the human body, and what we are doing in these days, what's happened last week. We have some recent update to share with you. So when light hit any kind of materials, and when laser hit tissues, only one of these 2 following can be happened. The light can be scattered or absorbed. No other way. It can go transparent, like it's not exist, visible light in glass. But in case it is doing any kind of interaction, it can scatter or absorb. In case it is scattered, we can see. This is the way you can see the presentation. You can see me, I can see you. We have light in the room. The photons go everywhere, scattered from our head, goes to our eyes, and we can see. If it's not visible enough, we are adding some contrast agents like fluorophores that we will discuss today, but other quantum dot stains, a lot of things. But it can be absorbed as well. Absorption, the energy goes to another processes. What kind? Many. But this can lead to therapy. If it goes to heat and it's specific to one point, you can do a very nice and efficient treatment. And for that, you can do it untargeted or using some mediation agents like photosynthesizer or gold nanoparticles. This is the other part that we are going to discuss today. Doing that by yourself, it's nice, but it's not enough. today, and I'm leading a group in Europe in the program of CMI, correlative multimodal imaging. Everyone has something very good on his hand, but if you are sharing it with the others and looking on the same sample from different angles, you can get much more. And correlating different imaging technique for specific purposes, we need to define what we would like to see now, and combine 2, 3, maybe 4 imaging technologies together, you will see something that you cannot get before. And there are 2 main approaches, holistic or multi-scale. And as Aristo said many years ago, the whole is more than sum of its parts. And this is the idea, to combine imaging techniques in order to go to implement biological logic gates. And this is the regular split between structure and function. And you can see all the imaging technologies that you can imagine that exist today. And we need to split them from functional to structural. And the issue is, what is the sensitivity that you are looking for, and how many molecules you have that you are looking and want to detect. And here are the techniques that are available, and we are looking somehow to combine them together. So this is a multi-scale information. If we are going from the function to the structure, we are getting this scale from the resolution to the penetration depth, and you have all of this scale. Our group, as a group, published this paper recently, a lot of citation already, because it's really practical. It's something that's good for every one of us that dealing with imaging, how we are thinking out of the box and combining more technology to what we know to offer. What I am combining in my lab is these 2 techniques. On the right side, we can see the diffusion reflection, DR. What is diffusion reflection? Very naive and simple technique that if you are illuminating light in one point and it's go inside, doing all the interactions, as we mentioned, absorption and scattering, anisotropy, reduced scattering coefficient, and so on, and is go back. If you are reading the profile of the light versus the point where the light injected in, you can extract the optical properties of the surrounding area. In case that you have high absorbance, you have less intensity that goes. If you have high scattered, it's go far away. And if you have something in between, you can extract all of this information. It started at the 80s with random walk theory, continue later on with the diffusion reflection and diffusion theory, and it's very practical even in these days, and we know how to build images based on that. The penetrations depends on the wavelength. If you are going to the near infrared, you can go deep to few centimeters inside the tissue, and it's something that can give you information from the volume. On the left side, we can see fluorescence lifetime imaging. Fluorescence, everyone knows what is this. It's a process of electron goes down from the S1 to S0 level. But we know to measure how long he is waiting at the S1 level. This is a fluorescence lifetime. In addition, we know to measure the rotation correlation. When he is rotating and emitting the light, we can calculate the rotation time. And if it's a ball, we have only one moment. If it's like this road, we have 2 moments. If it's other strange shape, we have the moment as the structure of this molecule. Time resolved measurements can measure things in picosecond level, and very, very precise. Unfortunately, fluorescence, it's on the surface regularly, but combining diffusion reflection with fluorescence imaging, you can see new things that you didn't see before. Few examples. We combined gold nanoparticles with fluorophores. The gold nanoparticles, we sense them inside the tissue for cancer, for other diseases, and combining them together, we are talking about almost 10 years ago work, we can see on the same image two different surface from fluorescence and volume of the diffusion reflection. We can even do metal enhanced fluorescence with this. Not only linking the fluorophore in one place, you can sense the distance of the fluorophore versus the gold nanoparticle. And this distance influencing the quenching or the enhanced. There is a phenomena called metal enhanced fluorescence that for well-defined overlap of the metal and the fluorophore, you will get higher intensity and not lower intensity. In this case, it's rhodamine B that enhance much more. If we are looking to fluorescein, it's only quench. It go from higher intensity to lower intensity. The rhodamine goes from low intensity to high intensity. And then we manage to detect, in this case, the border of let's say, tumor. And this was in phantoms. And we did things like that in vivo tissues. So as a background, we can combine, in this case, two things, diffusion reflection with fluorescence lifetime. No one combined them before, and see new things that was not discovered. But it's not enough. We know, everyone, that not so past history, we are talking about 40, 45 years ago, this is the first computer that was in the size of this hall, and he know to make a calculation up to 3 digits, 100, to make the basic algebra mechanism. And then we went to more advanced computers and for laptops that we are using everywhere. And today we have the mobile phones and more. But what is the limit and why we don't have this computer inside our body? Let's implement, like we are doing everything very minimized, biological computer gates that can be implemented and execute inside our body, detect problems and fix them. And doing that by all the imaging techniques that I mentioned before. But as all of us know, it's not trivial. Two main reasons for this. First, it's really hard to control. If we have a computer inside our body, it's difficult to get the mouse inside. More complicated, it's hard to insert. If you recognize this image, regularly, it's not easy to insert this kind of elements. But in case that we will build the computer according to the correct rules, we manage to do something. So I have a dream that we can, in the future, go inside our human body to build a machine, so this machine will get all inputs that they are having in this surrounding area. What is the temperature, pH, osmolarity, calcium level, whatever. All inputs, they will go inside this machine, and the machine will make the decision, now we need to do something like that. And this is a computer. The computer collecting a lot of inputs and doing an output, according to what we programmed. And in Israel, I don't know what is the situation here. We have a lot of bees, strange animal. Part people like them or dislike them, but they are doing something very interesting. The bees know exactly what to do without any direct communication, at least we don't know about communication like that, with the headquarters, with the queen at the headquarters. And they are making the decision, today we are going to this kind of flowers and we are collecting everything there. And the day after we are going to different flowers and it's working very well. We have the bee, go to the flower, doing the process, and the queen somehow controlling everything remotely without any physical connections that we can imagine or can see in our eyes. And it works. Now, let's try to change the field with our human body, the blood vessels. And instead of flower, let's go to a cancer tissue. And the bee, it's not a bee, but it will be an element that it's biocompatible and know what you need to do in case it is face this kind of situation. And when the bees meets the flower, it's attack and doing the work. In principle, it's easy. Now let's implement that. The idea is to replace the well-known computers that we are very regularly and operating in our clean rooms, and it's mainly built from silicon or more advanced material, and we will replace it with things that will be implemented inside the human body. And the same logic gate that can be implemented in silicon, we will implement in biological materials or biocompatible materials, and they will act and react according to the rules that we will synthesize them. Correct, today we have very sophisticated computer doing millions of actions in a nanosecond. This is not the situation now, but this is the reason I show you the first computer. It was not so far away. We are starting with something, okay? So let's do the starting. And what we are implementing in our lab is a combination of gold nanoparticles with fluorophores, because we have a lot of advantage of sensing and treatment with all of these two elements. And we are playing with quenching and metal enhanced and fluorescence lifetime conditions that it's easy to sense outside. Everything is not penetrating inside the human body and getting the results. For that, we need to build the building blocks. This is the secret. The silicons that did amazing work for our computers, we need to find the candidate for the building blocks for the body computers. And what we are using is metal nanoparticles and fluorophores that can be activated. An example for one fluorophore, it's FDA, fluorescein diacetate. It's very interesting fluorophore because by himself he is implementing some surrounding environmental conditions and cases. When the dye is in regular state, he is quenched. We have esterase side that not allow the dye to emit light. We found that there is still we have some light and we can measure something, but it's different story. When something happens in the surrounding area, for example, we have a cell. If this dye penetrating inside the cell, it starts shining. It's cutting the esterase side and it starts shining. So if we have esterase, it starts to be green. It's like fluorescein, regular fluorescein. So in order to detect esterase, you just need to use FDA. If the esterase exists, it will start shining. Not only esterase doing that, pH level. Small changes in the pH level, if you have higher pH level, it starts shining. So this is very easy dye to, it's biocompatible, it's very easy to use to detect things like that. Now, when we are activating this kind of fluorophore, we can activate it by esterase or by different pH level. Here we can see the pH level and we are getting the absorption and the emission level. And the idea is to adapt the intensity that we are collecting to the information that we have inside the body, inside the cell. So this is a regular intensity decay that it depends on multiple elements that we have inside. In case that we are talking only about FDA, that you have only two conditions. It can be quench or shining light after esterase. The sum will be only two, and we can split it to one element that we don't know the fluorescence lifetime, and we don't know how much, what is the volume, what is the percentage of the shining element or quenching element. And we definitely know that when the esterase is operating, we will have regular fluorescein. Regular fluorescein emit the intensity, and the average fluorescence lifetime is 4 nanoseconds. So we know the tau2 value, but again, we don't know the percentage, how much it's quenched and how much it's shining. So alpha, the percentage is unknown, alpha 1 and alpha 2, and we don't know the second fluorescence lifetime. Now, when we are playing with the pH, we can see very nice. Here it's a amplitude on x-axis with the amplitude of the free element and the tau1 value on picosecond. And we can see very nice, there is a curve that goes up, and we justified it in the theory and calculation that at the beginning, when no esteras, pH low, we have everything quenched. So it's A2, it's almost 0, and the quench, it's almost very short fluorescence lifetime. As it starts to shining, we have more percentage, and we have very good conditions. We have very nice light outside. So we are taking this element. This is the first building block, and then we are going to link it to something. And our friend is a gold nanoparticle. Regularly, we are not using gold nanosphere like this image, because we prefer to use gold nanorods. This is another part of the talk. Why rods? Because we have two peaks, one in 530 nanometers of the fluorescence of the localized surface resonance, LSPR. But in rod, we can go to, we synthesize that, we can decide where will be the second peak, and we will go from 600 to 900 nanometers. The penetration depth there, it's much higher. So the basic element, it's gold nanoparticles. We are coating it with PEG in order to eliminate aggregation. And at the end of the PEG, we have a cleaved peptide. What kind of peptide? Depends on the questions that we would like to answer. If we are looking for infection, we will use this peptide. If we are looking for virus, we will look for another peptide. The peptide, it depends on the application questions that the medical doctor or our colleagues comes and asking us. Then we are adding the inactivated fluorophore, like the FDA, like the fluorescein diacetate, and we will have the activated fluorophore. This is the basic element of the logic gate. Now, let's start to play with this. When we are synthesizing that at the lab and everything is relaxed, we will get 0, 0. It's quench and it's linked to the gold. Now let's add a high pH or esteras. Okay, this is the first condition. Something changed. Now it starts shining, but still quench or link to the gold nanoparticles. So this is 1, 0. Now let's say that we put a cleaved peptide that synthesized to caspase 3. In case that caspase 3 enzyme existing is cutting the fluorophore from the gold. So before we have shining fluorophores linked to the gold, and then we have shining fluorophore far away from the gold, and we have case of 1, 1. And no doubt that we have in between the case that we have caspase 3, but the pH it's not high, or no esteras, and we have the case of 0, 1. Here we implemented full logic gate. And by that, we can operate the operation, all kind of operations that you can imagine. We have 0, 0, 0, 1, 1, 0, 1, 1, and these are the conditions to detect them. And each area from this map, it's different operation. What kind of operation? And only in case that caspase 3 exists and we have high pH, operate the gate. So this is 1, 1. If we are, this is AND gate. If we want to have or caspase 3 or high pH, it's all the other cases. And all the others are the same for not AND, nor, XOR, and so on. We can operate all operations based on this element. Now you will ask me, it's not interesting. Only one gate, what we can do with this? We can, I will give a few examples, but today we are managing to operate 4 inputs and according to that 4 outputs, and doing it on sequence of 3 gates like that. Again, it's not a computer. We are still not there, but this is a way to arrive to real biological computer. So we are taking our building block and implementing questions according to what it's needed from the customer. Who are the customer? It's us, the medical doctors, the life science, and the other colleagues that we have. And this is the idea to make it a building block like that. And this is our biz. For examples that we are doing with this, I have several. Before we will go to the carbon dots, this is something that we are doing in our nano center. I will share with you recent results that we have with the EU project that we have about replacing knees of a human body. You know that we are growing and becoming old, and today it's very common that after 18, you need to replace knees. Replace a knee. We know today to print, we have very good 3D printers, and to print this element in very good, precise, and efficient way. But 92% of the people after 1 year need to come back to the hospital, getting injection of a drug after a huge infection that's happening because of high dense of the replacement knee. We got a very nice project from the EU that we implemented our logic gate, simple logic gate of 2 conditions. We took our gold nanoparticles, in this case it was a sphere, but it was empty. We insert inside the drug, and we implement the following 2 questions. 1, stress, physical stress. It's easy to detect stress on particles. Second, it's to detect infection. The medical doctors told me we are looking for TNF gamma. This is an indication, it's a knee when you have infection. I looked in the literature, I found the peptide that sensitive to TNF gamma, and we cleaved the peg with this peptide. Now, when we are planting a new knee for a human being, inside this printed element, they have our particles with a drug inside, and this 2 conditions logic gate. When a stress, physical stress starts and infection is starting, the drug released automatically. And it's eliminate, go to the hospital, not after you are suffering from bad conditions and you have heat. It goes all the time. These particles locating in the printed knee and just release the drug whenever it's needed. And this very, very naive and simple gate. Another gate that we are implementing these days based on carbon dots that we are synthesizing in our nano center, in the center itself, not only in my group. It's we are preferring again to go to red emitted in order to have very high penetration depths inside the body. And we characterized our unique gold nanoparticle carbon dots with DLS to see the size. We are talking about a few nanometers, 6 nanometers carbon dot, and we can link them again, like we did with fluorophores, to the gold nanoparticles, and the particle size is 200 nanometers. It's still small, it's still in the nanometer regime. The zeta potential indicates the same results, and we can see the absorption and fluorescence absorption coming from the carbon dots and the nanoparticles, and the fluorescence coming only from the carbon dots. And we can verify that we have the different wavelengths that are relevant for them. What we did, we took these carbon dots, you can see the TEM images again from our center, and the amine-coated gold nanoparticles, and linked them another gate that we built. And this how we get the images. It's a film. We are detecting the gold with the diffusion reflection. We can see the carbon dots by the film, and we implement this very simple switch of on-off, but it's reversible. It can operate on and off, and on and off. It's not only one time, one direction. So on condition, it's only carbon dots that emit fluorescence. It's off when it's linked to the particle, and it can be disconnected with trypsin. When the trypsin disappears, they are connecting again, disconnecting again, and it goes again and again. It's something that cutted and operating the gate. So we have carbon dots, gold nanoparticle, and trypsin. And this is something to the stomachs that we need to detect these cases. So we have the same elements as in the theory that we did before, and it's reversible output. It's happening all the time, again and again. It's not only one-time gate. This is the innovative part of this. Here you can see part of the publications that we are doing in this logic gate, biological logic gate, and we are waiting. It should be arrived already, but new publication from ACS Nano that goes in hopefully today or tomorrow. But something that happened last week in this another element that we are using, magnetic nanoparticles. We published this paper in April, and it's got the most viewed article in optics and photonics. It was highly viewed, and it's become editor choice, and we're really pleased to got it. And this is pure work that came out from our nano center. That we did it not as a PI, not as a professor, as people that operating the equipment and thinking about ideas, what we would like to do next. And these people that mentioning on this paper are a new group of establishing new material department inside our nano center to synthesize sophisticated and new materials for all types of use. So with this, I'm going to summarize my talk. The nano world is amazing. We have the big business, a lot of PIs doing many collaborations, and we have the small nano things that we are doing that can help our health and can help our surrounding area. It's very difficult, but it's worth it. This is a few words about summary, and I would like to acknowledge all the groups that supporting our research, and this is part of my personal group, not the groups that I show at the beginning that operating our labs. I would like to thank you for inviting us to be here with you today, and I open for question and discussion. I think this is the main reason to come here. So thank you very much.
Excellent talk, Dror. I guess you have accelerated your work so that you will see millions of lives, and maybe perhaps
hopefully together,
Win and BINA can work together in this effort. So I guess I'll first try to take some questions from the audience here in person. So please feel free to ask questions. Yeah, Emmanuel, please.
Thank you very much for the wonderful talk. Just a quick question. What have you had a chance to evaluate your nanoparticle system in vivo? I'm just kind of curious, what's the stability of your nanoparticles?
Everything is done in vivo. Everything. Okay. And the question if we are doing it on human or only animals. In vivo, it's the stability. It's very good. There are already companies. And you know, Nomi Halas that established the first company in that in the United States, and I think it solved very recently, I think 4 months ago, to get gold nanoparticles to healthy people. It's really big challenge to make it in routing, because we don't know what is the influence on the human body later on. But the stability of the particles are well defined. We are doing testing for months. We have some results after 2 years, and it's very stable.
So do you lose any of the fluorescence intensity over time? I'm just kind of curious.
Definitely yes. In case if you would like to get the signal, we are recommending to replace the stock after 6 months. The particles are very stable. The fluorophores, it depends. In the carbon dot, it's again very stable. The FDA is very stable, but if you are going to rhodamine 123, rhodamine G, it's quenched by himself. As implementations that we already have, I can show only short part of that. We started with melanoma and inside body cancer, and we faced the issue of getting right to inject it or even localized inject to healthy people. And then we went to oral cancer. Oral cancer today, you don't know if you can see some strange color in your tongue. There is no way to do anything, only to cut it, biopsy, and to send it to the lab. And what we did, we took our nanoparticles, we coated with specific antibodies to the cancer at the tongue. It's EGFR, EGFP, these are the receptors, and no need to inject. You just put it in the glass, insert to your mouth for 20, 30 seconds, wash your mouth, and then with simple elements, with a laser diode and few array of detectors, you can screen what is the percentage of particles that link to this suspected area. In case that you have a tumor, you will have high percentage of particles that link to this area. It is very simple, non-invasive way you can discover it. So it's very stable diagnostic. You can do it in routing element, yearly going to test that it's part of your insurance, and it's something that can works very well.
Thank you.
I'm wondering, often in these kind of gold nanoparticle agglomeration is kind of quite challenging. They may
Yes, but
agglomerate.
there is coating, and it's this was the question. It's stable. It's full.
So there is no such issue.
No,
there.
that's you're
Okay.
doing some kind of steering before, and it's very fun.
Oh, okay. So then.
Practically, it's fun.
Okay.
And I'm here in order to think about the collaboration for the audience here. If you have any kind of ideas, Google our BINA center and see our activity and comes with idea. Okay, if you want to do something together, this is the reason that Yossi and myself are here for today and tomorrow and maybe even.
Perfect.
Thank you again. Thank you very much.
So thank you so much again for this talk.